Let's go on to the next part. So we did the derivative of e to the x. We did the derivative of a to the x, right? So remember the derivative of a to the x is just a to the x, like e to the x, times ln of a, right? And if you think about it, that's consistent with e to the x, because if you say, well, e is just like any other number, a, right? Well, yeah, the derivative is e to the x times, if we did ln of e like we do ln of a, well, what's ln of e? 1, right? So it's the same. So it's consistent. Remember, math is nothing if not consistent, right? Everything should harmoniously work together, all right? Now, we're going to move on, right? Okay, you know what's coming because we're doing the exponential functions. Well, how about ln, right? We did the exponential. Well, how about logs? Derivative of ln of x, right? Okay, so suppose you have y equals ln of x, right? And now we want to see if we could take a derivative of this. Well, okay, anytime you have ln, mathematically, it's okay, it's allowed to take e, right, to raise it as an exponent e. So we say e to the y is e to the ln of x, which is just x, right? Because we do e to the y, e to the ln. So now let's take a derivative of this. The derivative of e to the y and the derivative of x, right? The derivative of both sides here. Well, what do we get when we do that? Here I get e to the y dy dx, right? Chain rule on the left-hand side, equals the derivative of x is still 1. So then what's dy dx? It's 1 over e to the y, right? If I just divide by e to the y, divide by e to the y. But now, what was e to the y from here? X. So the derivative of ln of x is 1 over x. Isn't that cute? You would never think to do that, but if you do, there it is. And it's all mathematically feasible, right? I mean, it's all mathematically correct. What you need to know is the derivative of ln of x is 1 over x, okay? That's it. So now, if u is a differentiable function, then the derivative of ln of u is 1 over u du dx, chain rule, okay? So, in here, so that u is the inside function, so then you do 1 over u times the derivative of the inside. You can move to this side of it. Can you see? Okay. All right, so the way it works is, suppose you have ln of some function, the inside function, all right? The derivative of this will be 1 over that inside function times the derivative of the inside function, okay? 1 over u du dx. Okay, all right. So find dy dx. Okay, so here I have ln of 10 over x. Let me rewrite that as ln of 10 over x, right? Which is what? 10x to the minus 1. Okay? So y prime, or dy dx rather, is equal to 1 over the stuff inside. So if the stuff inside is 10 over x, what's 1 over that? X over 10, the reciprocal, times the derivative of the inside, which is negative 10 x to the negative 2. So 110 cancels with 110. So what do I have? Negative x over x squared, negative 1 over x. Okay? All right, take a look at this one. Major chain rule here, right? It's ln squared of sine of x. Well, what does that mean really? This is really ln of sine of x squared, right? You can write the square either here or there. Okay, so now chain rule. We start with the 2. dy dx equals 2 ln of sine of x times. What's next? What's the second function? I did the exponent, now it's the ln, right? So times 1 over sine of x times the derivative of sine of x, cosine of x. Yeah.
Actually, it's sine like 2x.
Huh? Yeah, if it was sine 2x, then it would be times 2, right? Isn't that cool? So dy dx is, because now you have to take a derivative of ln of something. The derivative of ln is always 1 over the something, right? Huh? Yeah. So cosine x over sine x, whoops. Cosine x over sine x is cotangent x times ln of sine x. And that's good enough. Okay, let me say something important. One thing I saw, it was, you know, if it happens one time on a quiz, it's fine. If it happens like 3 times, then it's a trend, right? In any number, in any class. One thing I saw that is becoming a trend is when you're doing this, you're dropping this x here. So it's becoming 2 cotangent of ln of sine x. 2 completely different things, right? Because look at this. If I have sine of x times cosine of x, right? And suppose x is, guys, look up here for a minute. Suppose x is equal to pi over 3, right? Then what is this? Sine of pi over 3, cosine of pi over 3, root 3 over 2 times 1/2, root 3 over 4, right? Now, as opposed to what some of you guys had done is write it like this, sine of cosine of x, right? If you drop that x, now it's sine of cosine of pi over 3, which is sine of 1/2, and sine of 1/2 is, you know, some completely different value, okay? Sine of 1/2, like what's 1/2? It's pi over, it's a very small pi, yeah.
I don't know if this makes sense. I just think similar, but not.
Now, if you have an arbitrary real power, right? So again, anytime you have u to the n and you want to take a derivative, the exponent will drop and then you subtract the exponent by 1 times the derivative of the inside, du dx. So here, dy dx is, the exponent will drop, so it's root 2 x to the power of root 2 minus 1. That's it, right? Because what's root 2? It's 1.4. And what's the difference between that and 5? Nothing, right? Math doesn't discriminate between numbers like that. It doesn't differentiate between numbers like that. So the process will be the same. Similarly, suppose I have sine to the pi of x, right? That's like saying sine of x to the power of, instead of squaring it, or to the power of 3, I say to the power of pi. What's wrong with that? It's just to the power of 3.1415, right? So now dy dx, the pi will come down, times sine of x to the power of pi minus 1. Don't do weird things like 2.14, right? It's pi minus 1 times the derivative of the inside is cosine of x. And that's it. Okay?
Put the negative sine pi on the bottom of the equation, like root 2x to the root 2 over x, because the root 2 minus 1 is the same thing as x to the root 2 divided by x to the 1.
Oh no.
But we could, and it would still be fine, right?
It's unconventional. Yeah. Okay, so this is good enough for me. However, talking about AP, again, this will never be a free response question where